we are going to discuss about production of ammonia by Haber Bosch process. Industrially, ammonia is manufactured by the Haber Bosch process. Okay, you have to know what are the raw materials required to produce ammonia. Nitrogen and hydrogen gases. Those are the raw materials required for the production of ammonia. Then you want to know what is the method of obtaining nitrogen gas. Normally, nitrogen gas is separated by fractional distillation of liquefied atmospheric air. You can liquefy atmospheric air, then by fractional distillation you can get nitrogen gas. It has the production cost, therefore nitrogen gas has the production cost. If you focus on method of obtaining hydrogen gas, there are two methods. One is by cracking hydrocarbons or naphtha, we call it C6H14, or using methane, which is the main component of natural gas. If you look at the production of hydrogen from natural gas, we call it SMR, steam methane reforming. Normally, natural gas is used as a fossil fuel to generate power. Natural gas occurs in large quantities as underground ores in the earth. Normally, a small quantities of H2S is present in natural gas. This H2S disturbs nickel catalytic process which is used to convert methane to hydrogen. Remember, nickel is not the catalyst which is used in Haber process. It is used to convert methane to hydrogen. Then furthermore, hydrogen is formed by catalytic reactions after removing H2S in the natural gas. So we want to know how to remove H2S from natural gas. Normally, we can react H2S with zinc oxide where it gives zinc sulfide and water vapor. By that reaction, we can remove H2S gas. If you focus on SMR process, there are two steps. I can simply say first step, second step. Actually, there are names for them. The first step is actually reaction of methane and water vapor at temperature about 700 degrees Celsius to 800 degrees Celsius to produce carbon monoxide and hydrogen gas. Okay, that is the first reaction. So if you want to balance this reaction, you can consider carbon -4 oxidation state. Okay, this carbon +2 oxidation state, -2 to +2, it is 6 electrons. And hydrogen +1 oxidation state, 0 oxidation state, +1 to 0, you get 1 electron, but there are 2 hydrogens, therefore 2 electrons. Therefore, you have to multiply this one by 3. That's why you get 3 here. Okay, this 3 is from that. Now you know this side there are 6 hydrogens. Here 4 hydrogens and 6 hydrogens. That's how you balance this reaction. If you look at this process, you can see it is endothermic, plus 206 kilojoules per mole for the reaction. So this is an endothermic reaction. If you focus on the second step, the above gaseous mixture. What is the above gaseous mixture? CH4H2O reacted to get carbon monoxide and hydrogen. All CH4 does not react. Some will remain. So above gaseous mixture is further reacted with water vapor where formed carbon monoxide reacts with water vapor to give carbon dioxide and hydrogen. It is exothermic. So carbon monoxide is converted to carbon dioxide, and this one exothermic reaction. And I told you that all CH4 does not react. That means in addition to the second reaction, there is a possibility for a third reaction where methane reacts with water vapor to give hydrogen and carbon dioxide. That also possible. So basically there are three reactions. Then in first step, methane, water vapor, you are getting carbon monoxide and hydrogen. Second step, carbon monoxide, water vapor, you are getting carbon dioxide and hydrogen. And other than the second step, a third reaction can occur, that is methane reacting with water vapor to give hydrogen and carbon dioxide. Okay. Now, if you look at these reactions, if you consider this reaction also to be an equilibrium reaction, because it is a reversible reaction, we can apply Le Chatelier's principle. If you increase the amount of H2O gas, what will happen? When you increase the amount of H2O, the reaction will move forward in order to decrease the amount of H2O. Therefore, H2 gas concentration will increase. The yield of hydrogen in all reactions above can be increased by maintaining water vapor, more water vapor, and shifting the total reaction to the right. Same thing. If you increase the H2O gas concentration, to decrease that, forward reaction takes place, thereby hydrogen gas concentration increases. If you increase the amount of water vapor here, to decrease that, the forward reaction takes place, by that the amount of hydrogen gas increases. So that's what happened here. Okay, in these productions, always pay attention to the process. Okay, you should be able to explain what are the things happening here. You can explain these reactions by using thermodynamics also. Basically, delta G equals delta H minus T delta S. If you focus on this one, here 2 gas moles, 2 moles. Basically, there is no change, delta S. So if delta S is not changing, entropy is not changing because gas moles are remaining constant. At a constant temperature, definitely this value, there is no effect on this delta G equals delta H. Now you know second reaction is exothermic, minus value. Definitely, therefore, delta G becomes minus. That means at a low temperature level, this reaction takes place spontaneously. That's what you can say. So if you focus on this one, then you can say second reaction is exothermic, where delta H is a minus value. Since the number of gas molecules does not change, pressure has no effect. Further, the effect of T delta S on delta G is almost nil. According to about thermodynamic relationship, the exothermic second reaction is spontaneous even at low temperature. That is related to second step. If you focus on the first step and third step, okay, you can see in the first step there are 2 moles of gases giving 4 moles of gases. That means definitely number of gas molecules increase. Entropy becomes a plus value. This one, 3 gas moles giving 5 gas moles. Number of gas molecules increase. That means delta S becomes plus value. Actually, the first reaction is endothermic. The third one also actually endothermic. That means delta H is a plus value. This delta S also plus values. Now you know. Then delta G should be what? Delta G should be either 0 or plus or minus. Normally, if it is plus situation where delta H is plus, delta S is plus, the reaction becomes spontaneous or delta G becomes negative at, if it is plus high temperature. So you have to supply a high temperature in order to make these 2 reactions proceed. So you are given first and third reactions are endothermic. The entropy increases because the number of gaseous molecules increase to the forward direction. So with increase in temperature, the positive value of T delta S increases. Therefore, according to delta G equals delta H minus T delta S, in reaction 1 and 3, delta G becomes more negative at high temperatures. Therefore, endothermic first and third reactions takes place at relatively higher temperatures. Okay. Normally, reaction 1 is allowed to occur at high temperature, about 1000 to 1800 degrees Celsius. At that high temperature, the third reaction can take place because it also needs a higher temperature. And now I told you the second reaction takes place at a lower temperature. Therefore, when carbon monoxide is formed, in order to reduce the carbon monoxide concentration and yield hydrogen gas, more hydrogen gas, to reduce this one and yield more hydrogen, what we do is we allow the second reaction to occur at a relatively low temperature. What will happen when you decrease the temperature? Okay, this reaction becomes spontaneous at a low temperature even. Why? We found out earlier delta G is minus. It is minus. So, by adding water vapor to the hot gaseous mixture of carbon monoxide and hydrogen, its temperature can be lowered to around 200 to 400 degrees Celsius. By that, we can allow the second reaction to proceed. When the second reaction is taking place, you know, second reaction is exothermic, minus value for the delta H. So heat is generated, and that heat is used to obtain high temperature suitable for the first reaction. That's how these things work. I told you there are two methods of producing hydrogen gas. The other method is production of hydrogen by cracking hydrocarbons. So we consider hydrocarbons can be reacted with water vapor. Okay, it can be reacted with water vapor to give carbon monoxide and hydrogen gas. Okay, and carbon monoxide reacts with water vapor to give carbon dioxide and hydrogen gas. That's how the reaction takes place. If you want to balance, you can take that C6H6, therefore 6 carbons. You can put 6 here, 6 carbon monoxide. Okay, and there you have 6 oxygens, therefore it should be 6 water. They are altogether 6 into 2, 12 hydrogens, and 14, it is 26 hydrogens. That's why it became 13 hydrogens. Okay, you have to remember these two reactions. Actually, rather than the earlier method, this is more important. Therefore, remember these two reactions. Okay. And if you look at both processes given above, they release carbon dioxide gas to the atmosphere. So it is a problem. Okay. It contributes to the global warming. Now, we are going to focus on production of ammonia by hydrogen and nitrogen. Normally, the reaction related to the production of ammonia is nitrogen and hydrogen reacting to give ammonia, and it is exothermic reaction. It is exothermic. We are using a pressure of 250 to 300 atm, high pressure and high temperature. Okay, that's what we are using. Now, this is the reaction which is related to production of ammonia. This is exothermic and reversible. And under normal temperature and pressure, we consider this reaction hardly happens. It does not take place at normal temperatures and pressures. Why is that? Normally we consider it has high activation energy. That's why it does not take place at normal temperature and pressures. Okay, the activation energy is relatively high. you have to know what are the optimum industrial conditions. You have to know, you have to by heart these. Okay, temperature, a temperature in the range of 450 to 500 degrees Celsius, pressure of 250 to 300 atm. We use the catalyst iron. Remember, iron is the catalyst. Okay, catalytic promoters are used to increase the action of the catalyst. K2O, Al2O3, likewise. You have to remember these ones. And in the process, what we do is we use the high pressure. That means you have high nitrogen and hydrogen under high pressure, compressed mixture of reactants. Then we pass it over the surface of the catalyst iron to get converted to ammonia. Now, this reaction is reversible. I told you that it is reversible reaction. So when it is passed through the catalytic surface, it will have both hydrogen and nitrogen together with ammonia. So you get all three gases present. Therefore, there's a problem. That means you have to separate ammonia gas from this mixture. How can you separate ammonia gas? Normally, we cool the mixture containing nitrogen, hydrogen, and ammonia to a temperature at around minus 33.34 degrees Celsius. Normally, we consider at that temperature, ammonia liquefies. Normally, if you take nitrogen and hydrogen gases, their boiling points are minus 195.8 degrees Celsius and minus 252.9 degrees Celsius respectively, minus values. So if you reduce the temperature below minus 195.8 degrees Celsius, you can get liquid nitrogen. If you decrease the temperature below minus 252.9 degrees Celsius, you can get liquid nitrogen. But now the temperature is minus 33.34. That means you get only liquid ammonia, but nitrogen and hydrogen remains as gases. So by cooling this mixture, you can separate ammonia as a liquid, and this mixture of hydrogen and nitrogen can be separated from the reaction mixture. That's what we do. Okay, so gaseous mixture containing hydrogen and nitrogen and ammonia under high pressure, you can cool by decreasing the pressure suddenly in another chamber, then ammonia liquefies. So remaining hydrogen and nitrogen gases, then you can pump back into the reaction chamber again, where equal amounts of hydrogen and nitrogen that have been used to make ammonia, you can add freshly. Normally, now the temperature is minus 33.34. Again, after removal of liquid ammonia, gaseous mixture containing unreacted and newly added nitrogen and hydrogen, you have to heat to 450 to 500 degrees Celsius. So, the heat energy required to have this temperature can be supplied by combustion of fuel. That's how you get the heat energy. So, this is what happened in this process. Okay, what did we do? We used nitrogen and hydrogen and sent it to the reaction chamber. This is the pump to insert the gas into the chamber. You can send it like that. It has heating coil. You can increase the temperature and you can send it at a high pressure through the catalyst at a temperature of 450 to 500, where nitrogen, hydrogen will get converted to ammonia, but all three gases will remain. Okay, because all nitrogen and hydrogen are not converted to ammonia. All three gases pass through the reaction chamber. Okay, then you can take them into another chamber where you can use a heat exchanger to reduce the temperature, and by that you can get liquid ammonia, and remaining nitrogen and hydrogen you can reuse in this process, where you get liquid remaining nitrogen and hydrogen gases. You can combine with the newly added hydrogen and nitrogen, and again continue this process. That's how the process takes place. Okay, you have to remember this one. Then remember, in the Haber process, carbon dioxide is produced at the step in which hydrogen is produced, and also during the burning of fuels to gain high temperature. You know, carbon dioxide is a greenhouse gas. So due to these processes, carbon dioxide is released to atmosphere. So globally, when 1 ton of ammonia is produced by overall process, actually about 2.9 tons of carbon dioxide is released to the atmosphere. Compared to the releasing of carbon dioxide to atmosphere by other processes, approximately 1.4% of it is by ammonia production. Okay. And you have to know the reasons for these things. These are very, very important. Okay. In your learning outcome, they expect you to know these things in detail. You should be able to explain this. Reason for mixing nitrogen and hydrogen according to their stoichiometric ratio in ammonia production. Why are we mixing in 1:3 ratio? You know, it has nitrogen gas, hydrogen gas, okay, giving reversible reaction, and all physical states must be included. Okay, though I don't write here, physical states must be there. What can you say? You want to spend money on production of nitrogen, hydrogen. Why do you add excess wastage? No need. Both processes you have to spend money, so don't add in excess. And if you add something in excess, how these reactions takes place? These reactions takes place with the aid of a catalyst. Okay, in a catalyst there are places for these gases to get combined to the catalyst. Now if you add one gas in excess, all these places will get covered by that gas, so the other gas won't have any chance. Okay, so that's why we should mix it in 1:3 ratio. And why are we using the catalyst? To increase the yield? No. We use the catalyst to increase the rate of both forward and reverse reactions. By that, we can reduce the time taken for the completion of the product. Okay, that's why we use the catalyst. So, if you go to details again, it is you are given, since some cost has to be borne to produce nitrogen gas and hydrogen gas, they are not mixed beyond their stoichiometric ratio, and this prevents wastage of raw materials. And further, if one gas is used in excess, it would be absorbed by the surface of the catalyst, covering the surface completely. Coverage of catalyst surface by one gas reduces the chance for the reaction to occur, and both the gases need to be absorbed to the catalyst surface. Use of the catalyst decreases the time to reach the equilibrium, and based on all the factors, nitrogen and hydrogen gases are mixed in the optimum ratio 1:3. Okay, next one. Why do we need 450 to 500 degrees Celsius temperature? You have nitrogen gas. You react it with hydrogen gas. You get ammonia gases. Physical states must be there. Enthalpy minus. What about entropy? 4 gas molecules, 2 gas molecules, entropy decreases. The number of gas molecules decrease means entropy decreases. Delta S is a minus value. If delta H is minus, delta S is minus, we consider delta G should be plus O minus O 0. Earlier I told you, plus situation you get high temperature delta G minus. If it is minus situation, low temperatures, okay, if you use a low temperature, the reaction becomes spontaneous, delta G becomes minus. Then why do we need 450 to 500, it is a high temperature. Thermodynamically, low temperatures are favorable. We'll use equilibrium Le Chatelier principle. This is an exothermic reaction, delta H is a minus value. When you increase the temperature, what will happen? The system tries to decrease the temperature. To decrease the temperature, the endothermic reaction should take place. Endothermic. Which reaction? If this one forward reaction is exothermic, okay, definitely the reverse reaction should be endothermic. Then reverse reaction should take place. That means if you increase the temperature to a higher value, the reverse reaction takes place, not the forward reaction. Then we should have used low temperatures. But remember, this is an industrial process. It depends on the efficiency, the rate of the reaction. Though these two indicates that we should use low temperatures, actually using low temperatures, the rate of the reaction is very low. I told you earlier, this one has high activation energy. So the most favorable temperature range is 450 to 500 to maintain a good rate of this reaction. Okay, so that one you have to remember and you have to explain. If you can't remember details, you can't explain this one. Sometimes you will say something else. You won't get marks if you tell something else. You have to explain in detail. So you're given the reaction is exothermic, so its delta H is negative. When the reaction proceeds, entropy decreases because the number of molecules decreases. Hence, delta S of the reaction is negative. Thus, T delta S is negative and minus T delta S is positive. Therefore, with the increase in temperature, delta G changes from negative to positive. The fact that high temperatures do not favor the forward reaction can also be explained by Le Chatelier's principle. On increasing the temperature, the spontaneous nature of the reaction decreases. Thermodynamically, when the spontaneity decreases, the yield increases. So, yield decreases. So, to increase the yield, the temperature should be decreased. But when the temperature is decreased, we consider the rate of the reaction decreases and the efficiency of the entire process declines. A temperature of 450 to 500 is used to maintain an optimum efficiency. And remember, the ammonia yield obtained under these conditions is relatively low. What do we do? We have designed the process, okay, so that the unreacted hydrogen and nitrogen gases are brought into the catalytic cycle again and again. That's what we do. So despite the fact that the amount of ammonia yield by a single step is small, the process as a whole gains a high yield because it has been designed to carry out by a number of catalytic cycles. Okay. Why do we need 250 to 300 atm pressure? It is N2 gas reacting with 3H2. You need to write physical states giving 2NH3 gases. If you increase the pressure, what will happen? System tries to decrease the pressure. Le Chatelier principle. To decrease the pressure, here 4 moles of gases, 2 moles of gases. It moves to the side which is having less number of gas molecules, this side. So that means if you use a higher temperature even, it is very good. But maintaining higher temperature chambers very difficult, cost a lot. So the optimum temperature is this temperature. So you are given, according to Le Chatelier's principle, higher pressures favors the forward reaction, but the maintenance cost of the plants withstanding high pressure is high. Therefore, at present, a pressure of 250 to 300 atm is used. Okay. And maintenance of reactant concentrations high level and product concentrations at lower level results in high yield of ammonia. Remember that also. You have N2 reacting with H2 to give NH3 gas. You know, when you increase the concentration of reactants, either this one or this one, what happens? According to Le Chatelier principle, system tries to decrease them, so the forward reaction takes place. And when you liquefy all ammonia that is formed, ammonia concentration decreases. To increase that, the forward reaction takes place. We are using those tricks to increase the production of ammonia. So you are given, this can be explained by the Le Chatelier's principle. This requirement is fulfilled by introducing nitrogen and hydrogen into the reaction chamber from time and removal of ammonia by cooling the gaseous mixture containing ammonia and liquefying the gas. Finally, you have to remember the uses of ammonia. Normally we use ammonia for the production of nitric acid, fertilizers, nylon, and we use them in petroleum industry to neutralize acid constituents of crude oil because ammonia is a weak base. Used in water and wastewater treatments such as pH control in solution form to regenerate weak anion exchange resins, and used as a refrigerant, and used in rubber industry for the stabilization of natural and synthetic latex to prevent premature coagulation.